welcome to Math 408, L functions and sphere packings. This is either lecture 27 or 28. It seems to be different from the other class I'm teaching, so I think I'm going to just bump this up to 28 so the numbering aligns. And so the purpose of today is to talk a little bit about data integrity, about what do you expect to happen. And this is inspired by one of the problems that we were discussing last time, where we had this wonderful function which came from a discrete optimization. F of x was, I think, n over x to the x, and the max was either the floor of n over e or the ceiling of n over e. And the question was, how often was it each? And what would be the natural conjecture that you would make? 50-50. But there's a lot of ways it could be 50-50. It could be 50-50 by having a streak where it's the floor, followed by a streak where it's the ceiling, followed by a streak where it's the floor, or it could be a lot of rapid fire alternating. And so I don't want to give it away for those of you who haven't started doing the numerics yet. But what might you expect? Would you expect streaks? If so, how big of a run do you expect? Consecutive values where one of these wins. Do you expect the run length to be increasing as n is getting larger? Then maybe you'll have more of a window where the ceiling wins, and then you have a longer window where the floor wins because n grew. Or do you expect that the runs are going to be essentially independent of n? So this is related to a lot of questions you can ask in probability. And these all come down to, if I have a set of data, do I think it was naturally generated, or do I think that there was something nefarious going on? So frequently a professor will split the probability class into two and say, I want half of you to flip a fair coin 100 or 200 times, and I want the other half of you to just simulate. And usually you can tell. So what's the first test you look at to see if a data set is reasonable for this problem of flipping a coin? Proportion of heads. So the proportion of heads should be about 50%. And if you know the central limit there, that gives you some idea of the fluctuations you would expect. If you have n tosses, you expect fluctuations of size square root of n. The standard deviation is actually the square root of n times 1/4. And so that gives you an idea of the scale. The next thing you can look at is for runs, for lengths of consecutive heads or tails. And so I want to talk about the longest run, or just runs in general. So flip coin n times probability of a head equals p, probability of a tail is 1 minus p. So an application of this is roulette in Vegas. So how many of you have never seen roulette or know what roulette is? Okay, so you have a win, you spin it. Normally there's 18 reds, 18 blacks, and 2 greens. And those 2 greens are wonderful for the house because they pay as if it was your 50-50 chance of getting red or black, but it's not quite a 50-50 chance. It's close. If you want, we can consider the simplified world of roulette where the probability of getting a red is half. And I will give you a strategy that is guaranteed to make you as rich as you want. Now you might ask, why am I still here teaching if I have a strategy guaranteed to make as much money as I want? Because money is not everything. Money is not exactly. And the ability to interact with Williams students, even if it's masked in 6 feet distance, and even if some of you have to be remote, is just worth more. So here's the strategy. Bet $1 on red. If red, you're up $1. Else down 1, bet 2 on red. If red, how much are you now up? 1. If black, down how much? 3, and now you bet 4. And then lather, rinse, repeat. And this is called double plus one. Eventually, you get a red, and eventually you net $1. And then lather, rinse, repeat. Do this as many times as you want to make as much money as you want.
Like that, there's some problem where you're flipping coins. But like, how much do you pay to play a game where
Yes.
I give you like 2 to the end
Yes.
for each coin?
Yes. So what is the problem? Why can't I do this in Vegas?
It's not 50-50.
Well, but that just means it could take longer.
You need deep pockets.
So you need deep pockets. You also need more than just deep pockets. You need balls, nerves of steel, or whatnot when you're down $2 billion to then put in the $4 billion bet. So the solution to this is the U over AH, the eccentric rich uncle or aunt hypothesis. So I posit the existence of a family member who has unlimited money. They will not give you any money directly. That's wrong. But they will stake you. And so however much money you need, you just go to your eccentric rich uncle or aunt and say, hey, I need $2 billion per bet. Sure, here you go. And so they will stake you so you never have to worry. What's the other issue?
There can be betting limits?
Yes, excellent. And, again, I don't want anybody to worry that they are showing too much knowledge of gambling in questions like this. This is, of course, just all theory. If anybody wants to apply any of this, let me know. I know other Williams students who are happy to investigate.
What else is that?
Yeah. So what does it mean by betting limits? You have a table max. So you have a min and a max bet. And so you might be at the point where you want to bet $64, but you can only bet 50.
That's
And
the high stakes roulette tables.
well, but there's only finitely many tables. And so at some point, you reach a problem. And so what happens is when you win, how much do you win?
$1.
$1. You've seen trading places, $1. It's not a huge amount. But when you lose big. Is it possible for a lot of people to apply this strategy and actually make money in the casino?
Yes.
Potentially, yes, and we'll actually do the calculation. And so it is quite possible for some people to apply this profitably. But someone has to pay for Mr. and Mrs. Smith's suits. Vegas is not in business as a charity.
Yeah, you tip I guess you tip the spinner, about 2% or whatever.
So there's a lot of things like that, but still the house needs to be making a cut or it's not going to stay in business. And so the question is, at what point do you have so many consecutive failures that you go bust? And so we want to calculate what is the probability of, say, getting 5 consecutive blacks. So what is probability of 5 consecutive blacks if spin n times? I have never gambled in the Vegas casinos. In the old days when you could actually fly to different parts of the country, I have occasionally flown through Las Vegas. And I love how they have, I think, slot machines in the airports. The slot machines have some new features. I'm not sure if this is in the airport or if it's in the casinos. They tell you the results of the last few spins. And the reason is that...
That's awful.
Well, okay, why is this awful?
It's useless information. I mean, assuming they're fair.
Assuming they're fair, but there's often 2 types of morons in gambling. There are those who believe, wait, it's been black for 5 consecutive times, 6 consecutive times. I'm going to bet on black. Black is doing well. And what's the other type of moron? Red is due. I'm going to bet on red. Vegas doesn't really care which category you fall under. They just care that you fall under the category of, I will put down money. The more people who put down money, the better it is for Vegas. And so they will provide this useless information, as you remarked, to get people to be more willing to gamble. 12 consecutive blacks. Red is due. Or I got to cash in before the black streak is over. So we want to calculate what is the probability that we have 5 consecutive blacks, or the probability we don't. Does it matter which one of these I calculate? No. If I know the probability that I do, the probability I don't is 1 minus. One of them is going to be easier than the other.
Are you ignoring green?
We can adjust it by having p as the probability.
Yeah, so shouldn't it be 1 over 1 minus p, the fifth?
Well, but remember, you have a whole string of n rolls, n spins. You just have to avoid 5 consecutive blacks anywhere. So before we solve this, I want to talk about trying to estimate the answer. Can we get some lower bounds or upper bounds? And we will try to calculate the probability we don't. It's a little bit easier to calculate the probability we don't than to calculate the probability we do.
And for a lot of that, it's 0.
Good, okay, so for what n is it 0? Unless they go to 4, we know, so we know the initial conditions. Great. Any idea what's going to emerge from this? What kind of relation?
Recurrence.
Recurrence relation is going to emerge. Before I solve that, let's look at, let's take n equals 100. And we can look at blocks of 5. What's the probability I don't have 5 consecutive blacks in this?
1 over 32.
1 over 32. So 1 over 32, I'm sorry?
It's 31.
So 1 over 32 I have, 31 over 32 I don't. And it's the same throughout. So if I multiply all of these together, how many blocks of 5 do we have?
100 over 5.
100 over 5. I like n over 5, yes. Is this going to be an upper bound or a lower bound for the probability we don't?
Upper bound. Upper.
Okay, why upper?
Because there could be blocks in between.
Right, we could be black, 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 red, black, red, red, black. Almost did red, red wine, but okay. So this is going to be an upper bound for the probability we don't. So you can actually calculate this and see, what is this? How could we get another upper bound? Well, does somebody have a calculator who wants to calculate 31, 32 to the 20? So if I want to write as 1 minus 32 over 30, 1 minus 132 to the 20th, you might want to approximate this as 1 minus 20 over 32. Then the next term would be 20 32nds squared. And we would have over 2 factorial, because it's really, oh no, it's going to be 20 times 19. Yes, it's really, that's approximately 20 times 19 over 32 times 32 times the 1/2. The smaller this is, the better approximation this is going to be. But you can already see a little bit over here that, 12 32s, it's going to be a little bit more than that. Anybody calculate what 31 32 to the 20th is?
I'll do 31. Someone else 30.
All right. 31 divided by 32 to the 20th is, helps if you have both parentheses.
53.
52.99%. So this is not quite enough to know if we have a 50-50 chance. But given that this is a really bad upper bound, I would expect with 100 tosses the probability is going to be much less than 53%, much less than 50%. But it's nice to get a quick ballpark estimate. What could we do to get another estimate that's better than this? How could you tweak this argument? And again, one of the reasons I'm doing this problem is I really care about the thought process. I care about trying to get good upper and lower bounds. How could you improve this argument and get a better result?
Would you like alternating 3s and 2s?
Well, if you have blocks of length 3, that's never going to be enough for 5 in a row.
I'm saying do like 3 then 2, then 3 then 2.
What do you mean by
Not
3?
calculate cleanly.
What do you mean by 3?
A block of 3, then a block of 2, and calculate adjacencies from like these.
But if you're gonna do that, why don't you just do block of 1?
Block of what?
Like 1.
Well-
He's saying you could split it up, then.
Block of 1 is the wrong size to do. We started with a block of 5. What should we try next?
Block 10.
So one could do a block of length 10. 6 is a little bit easier to do first, but you could do a block of length 10. Is it possible to have 2 strings of length 5?
Yeah. No. Yes.
Yes.
2 distinct anyway.
Two distinct. And so the problem is, as you get longer, it's possible to have multiple strings of length 5. If we have a block of length 6, I could actually have 6 in a row. Let's just do blocks of length 6. What's the probability we have in a block of length 6? You could have all 6 being,
Block.
which is 164, right? And then you could have red followed by all blacks, or 5 blacks followed by a red. So 3 over 64 you have, 61 over 64 you don't. And so now, the probability you have should be less than or equal to 61 over 64 to the 100 divided by 6. We want to round, so we would want the floor. We want the floor because the last partial block can't hurt us. So how many times does 6 go into 100? 16. So we can replace this with 16. So this now improves to 61 divided by 64 to 16 is 46.39%. And so that's already enough to tell us that the chance of this happening is greater than 50%. The longer we make this block, the better the result is going to be. If you did a block of length 10, how bad would that calculation be?
You could have, what, 5 different?
It's not that bad. So homework. Do block length 10. There are 2 ways you could compute this. What are the 2 ways you could compute this?
Recursively.
So you could try to do recursive.
Count how many do have a 5 and subtract.
Yep. And how would you count how many that have?
Yeah, that was what, 5 times 5.
4 over 5.
So one is you could structure your where must your block of length 5 start? How long could it be? How else could you find the answer? And this is one of the reasons we're doing this, because this does not seem to be on your radar as something you can do.
Simulate it or like
Okay, not simulate it. Code it. No, it is not cheating.
So you're fine if I just code it up and then say like, oh, it's this.
Yes. For calculations like this, absolutely. When I was a kid, I read some books that my mother read when she was a kid. It was the Danny Dunn series. I don't know if anybody else has ever heard of the series. So his mother is a maid to a professor, and he is always getting in trouble. And I think the books were written in the 1950s, and in one of the books, the professor invents a computer. And so the kids start to play with the computer because they realize, wouldn't it be great if we programmed the computer so it can do our homework, so that we don't have to do our homework anymore, we can just have fun. And what do you think the moral of the story is?
It's harder to code it than it is.
Close.
Well, they learn to code, so then they just, yeah, like they just learn to code instead of like actually learning how to code.
Close, but by learning to code it, they actually had to learn the material enough to be able to code it. But if you can code something like this, this is a very straightforward code. You have 10 variables. Each one can be yay, nay. And then the question becomes, how would you calculate if you have 5 consecutive blacks and something like that? So it's not a bad idea to just think about how would you actually write the code efficiently to see, do you have something like that? There's a couple of things you can do. It doesn't have to be the most efficient code, because how many times are you running it? Once. How fast are computers? For something like this, the runtime is negligible. When I was in the American Institute of Mathematics as a postdoc, many summers ago, actually Professor Goldmacher was a student of mine back then. Yep.
Here?
Yep.
He went here?
Nope.
Princeton?
He went to Princeton, and he came with me to the institute for the summer. We were told of the following problem. You have the numbers 1, 2, 9, and you form 3 numbers. So you use each number once and only once. And so, B, C would really mean 10 times B plus C. And if you choose the numbers appropriately, you can get the sum of 1.
Why is it 10?
I'm sorry?
Why is it 10 times?
No. So if it's 9 over 37, it's 9 over 37.
Oh,
I'm just writing it as concatenating the digits. And so the question is, how do you arrange the digits 1 through 9 to do this? I am surrounded by some of the best number theorists in the world, and they start proving results about where certain numbers have to go. I write the code in Mathematica. There's some simplifying assumptions you can make to have the code speed up. Yes, what can you assume?
No, if the fractions is greater than 1.
I'm sorry?
No, if the fractions.
So one thing is you could actually assume none of the fractions are greater than 1. All right, but that's actually going to be forced on you.
Is it?
Yeah.
You have a 1-digit numerator and a 2-digit denominator.
Wait, it's not B times C.
No, that's what I'm saying. It's 10 times B plus C. So like 3 over 17 plus 5 over 49 plus 8 over 26.
I was like, 9 over 2, that's bigger than 1.
Right. How many possibilities are there?
10 factorial.
Nope.
9 factorial.
9 factorial. 9 factorial is only on the order of 300,000. For us, that's bad. For a computer, it's a piece of cake. Without loss of generality, what do you know about the digit 9?
A, B, or C.
It's A, B, or C. Without loss of generality, you can always assume it's one of the first few. And you can do case 1, 9 is A, case 2, 9 is B, case 3, 9 is C. And that replaces a 9 in the multiplication with a 3. That's wonderful. That's a 67% savings. It would take more time to code that than you would save in running the code. I'm only running this program once. It makes no sense to code it efficiently because it runs so fast. So I won't assign this, but if you want, write the code and find out, what is the solution. How many solutions for these fractions do you think there are?
1.
3 factorial.
3 factorial, up to symmetry. And so you could say if you want that the fractions have to be maybe ordered in increasing or decreasing order so that there will now be a unique solution. But for some problems like this, it's not worth coding efficiently. And again, this is a senior seminar. One of the things I hate about senior seminars is you never know what background students will have, and you could have backgrounds all over the place. But one of the things I love is you often have tremendous freedom in terms of what you get to do. you're not going to use most of the physical content that you learn in this class. But if you, I'm sorry? It's a fact of life. But the way to think about problems, that's going to be extremely useful. And so for a problem like this, one of your first thoughts should be, let me code it. Now, of course, it's actually not that hard to go from coding this to could we just code the original problem? Could we calculate all the possibilities? What do you think? Could we calculate how many possibilities are there for the string of length 10? 2 to the 10th. How big is 2 to the 10th? 1,000. 1,000 is not bad. You know, computer, it's not even going to work up a sweat. But if you wanted to do all 100, you would have 2 to the 100 possibilities. That's 2 to the 10th to the 10th, right? Which is approximately 10 cubed to the 10th, which is 10 to the 30. So you cannot do this by brute force.
Well, you could just play the game, right? You could just...
That won't be a proof. What would it be? What could you do? Instead of coding it, you could Monte Carlo simulate. And you could simulate this so many times that you would essentially have the answer to whatever precision you want, as long as you don't want too much precision. You know, if you want 2 or 3 digits, that's not going to be hard to simulate this enough times to get 2 or 3 digits. But you will not be able to get the exact answer from the simulation. One of the things that we might also want to see is how would things change as we change the probability. If you don't have a theoretical proof, you often lose parameter dependence. But you know, going forward, it should be on your mind. What tools do you have? And if you can solve a problem using a different tool than is expected, that's absolutely fine. So, how would we solve this exactly? So let's let Q of n be the probability no 5 consecutive blacks when spin n times. And we want to calculate this. And you already told me we know Qn equals 1 if n is less than or equal to 4. So we start here at n. We have 2 possibilities. With probability p, we get a black. With probability 1 is p the red or?
Doesn't matter.
I think we're doing p was red. Well, it doesn't matter. So, which way do you want to do it?
P red.
All right. So with probability p, we get a red. With probability 1 minus p, we get a black. What is the probability? We have 5 consecutive, we don't have 5 consecutive blacks when we spin n times, given that the first spin is red.
It's just Qn minus 1.
It's just Qn minus 1. This probability we don't know yet. We spin again. 1 minus p, p, red, black. What's the probability if we start black, red, that we don't have 5 consecutive blacks and n spins? Qn minus 2. P, 1 minus p, red, black, Qn minus 3. P, 1 minus p, red, black, Qn minus 4. We're running out of space on the board. P, 1 minus p, Qn minus 5, and this is a red. Oops. I've run out of space. Is that a problem?
No. Isn't it 1?
It's not 1. What goes over here? Black, 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 black.
Oh, black, black, yeah. 1 minus P. No.
We're trying to calculate the probability we don't have 5 consecutive blacks,
Oh, 0.
given that we start off with 5 consecutive blacks,
0.
right? If we had done it the other way, then it would have been 1. And so this gives us the recurrence relation. Q of n is equal to P Q of n minus 1, right? Plus 1 minus P times P Qn minus 2, plus 1 minus P squared P Qn minus 3, plus 1 minus P cubed P Qn minus 4, plus 1 minus P to the 4th P Qn minus 5. We now have a recurrence relation of depth 5 and 5 initial conditions. I'm sorry? We could do that. Now we know the general solution will be, Qn will be alpha 1 root 1 to the n plus alpha 5 root 5 to the n. The roots will be distinct. The problem is that, well, this is a quintic. And in general, we're not going to have a nice explicit formula for the roots of a quintic. But we can approximate the roots. Newton's method, we have ways we've seen to approximate the roots. We can come up with a really good approximate formula. Or we could just do this and just recursively calculate the stuff. It's not going to be that bad. I think it's around an 81% chance that you fail. So that if you spin 100 times, you're calculating the probability of 5 consecutive heads. It's quite sizable. And this is one of the facts people don't know when they're creating fraudulent data. That what is the distribution of the longest run? And so a lot of times I have my students read a beautiful paper by Schilling. I think it won some awards for just great exposition about calculating the distribution of the longest run of heads. If you're thinking of writing a sequel paper, the longest run of tails, please don't. What's amazing is it is an incredibly tight result, where the length of the longest run, if you have a fair coin, it's on the order of some constant times log of n, which is not surprising. As you toss more and more times, the longest run grows, but the variance is bounded by 4. And that's shocking that the variance is not growing on n. You have tight, like exponential of exponential coming in terms of what the bounds are like. E to the negative e to the. And it's remarkable when you see a double exponential occurring naturally in mathematics. So there's a tremendous amount of good math here. What you might want to do is, could you try to calculate what is the probability of having 6, 7, 8? We could do a very similar analysis. But it's hard to look at this and see how things are going. Frequently in probability, we often calculate the cumulative distribution function, the probability to take a value up to a certain level. And so if I can find the probability I have at most 7, and I can find the probability I have at most 8, or at most 6, I can then probably calculate the probability I have exactly 7. One of them, I use 2 out of the 3. I know 7 is one of them. You either use the 8 or the 6, depending on how things are phrased. So any questions on this? So there is the theory that would, it's a little bit more involved to calculate the expected longest run. And that would be a great statistic to look at when you see a data set as to, is this natural? If you ask people to give you a result of flipping 5 coins randomly, 5 fair coins, what do you expect to see from people?
Wait for their guess for longest run.
Yeah, so you ask people, give me the result of flipping a fair coin 5 times. Something like that. So you would expect probably about 2 heads, 2 tails. It would be interesting to see how many people would have all tails, all heads. Those would look suspicious. But about how often should those happen? 1/16. And so people don't have a good sense. There's, of course, a difference between looking at a huge number of things and looking at just one. Every string is as likely as every other string. But if you have a whole slew of strings, most of them will have a similar property. So the other thing I want to talk about, which will be very useful for when you're looking at your data, is the alternation between heads and tails. So how many runs do you have? And so we will assume we have, n1 heads and 2 tails. And this is just being a little bit general. And so we'll let n be n1 plus n2. What we might do later is we might say we have big N coin tosses, and the probability of a heads is p. But what I can do right now is I can do the analysis assuming I have n1 heads and n2 tails. And then I can just change the analysis later by, for each pair n1 and 2, I weight it by the probability it happens. So what I want to do is talk a little bit about generating functions. So we did Benet's formula with generating functions, right?
With factorial?
Yes. So generating functions. So the first, I'm going to give a story proof. The sum k goes from 0 to n of n choose k squared. Has anybody seen this? This is a very famous sum. It's sometimes rewritten as the sum k goes from 0 to n of n choose k, n choose n minus k.
Oh. Oh, yeah. We get this. This is one of our homework from probability.
It's a great problem.
2n choose something.
Yes. What is it? It's 2n.
One number 2n choose something.
Okay, well, great. So you know it's 2n choose something. What would you guess? It's 2n choose 2n choose n. So n choose k equals n choose n minus k. You can prove this by algebra. You can also prove it by story by Dr. Seuss. How many types of sneetches on the beaches are there?
2.
2. And what kind of sneetches on the beaches are there?
Sneetches.
There's stars on their bellies, and there are those that don't have stars on their bellies. And of course, we learn at the end of the day, it doesn't matter if you have a star or you don't have a star.
You're still a sneetch.
You're still a sneetch. So if you choose k people to be the exclusive group, that's the same as choosing n minus k to be in the excluded group. So that is a story that n choose k is the same as n choose n minus k. One way to prove this is you could prove it as a story. So you have 2n people, and you want to choose n. How many ways can we choose n people from 2n people? 2n choose n. Now let's say we have n Red Sox fans and n Yankee fans. How many ways can we choose n people? Okay, yes, but why?
Yankee fans are the same as Red Sox.
No, Yankee fans are not the same as Red Sox fans.
How many Red Sox fans you got picked?
Good. So let's sum k goes from 0 to n. That's going to be how many Red Sox fans we pick. And there's n choose k ways to choose k Red Sox fans. We need to get up to n people, so we're stuck with n minus k Yankee fans. So these two have to be the same. So this is proof by story. There is another way to prove this. So x plus y to the n times x plus y to the n is x plus y to the 2n. This is the same as the sum L equals 0 to n n choose L, x to the L, y to the n minus L, times the sum, n goes from 0 to n, and I'm going to do it as n choose n minus m, x to the n minus m, y to the n. I could have done it the other way. I just know where the algebra is going, so I'm just going to try to make my life easy. And the other one is just a sum. K goes from 0 to 2n. 2n choose k, x to the k, y to the n minus k. What do I know because these two polynomials are equal? Each coefficient has to be the same. Why is that the case? Have you ever formally proved that if you have two polynomials that are equal, then the coefficients must be equal?
Yes.
Okay, when did you prove that?
Abstract, I think.
Abstract?
Yeah.
So how would you start the proof?
Subtract the two polynomials.
Okay, so subtract the two polynomials, so you now have a polynomial that's equal to 0 always.
Yep.
Well, but we have several variables.
Some of them aren't equal.
If there's a coefficient that's not equal, you can just plug up the x and the y corresponding, and it's going to go off to infinity. So that's a good way to handle it. You know, it's going to be 0 everywhere, but if one of the coefficients is not 0, then consider the one that has the highest sum of x and y, take x equals y, and that goes off to infinity. So we know that the only way they can be equal is if they're equal term by term. So if we look at the x to the n, y to the n term, the coefficient of that is 2n choose n. And how would I get an x to the n, y to the n? Well, whatever I choose for L, m has to be the same. So the x to the n, y to the m is from m equals L. And so that would give you, the sum, L goes from 0 to n choose L, and then you would have n choose n minus L, x to the n, y to the n. And so this is the proof by using polynomials. So for our analysis of runs, it's going to be very useful to have polynomials like this, and to say that a polynomial must be equal to another if and only if the coefficients are equal. Sometimes we're going to want a little bit greater flexibility. We might do x1, y1, x2, y2, and then eventually in the problem set x equal to y, x1 equal x2 equal x, y1 equal y2 equal y. The last thing I want to just quickly mention before we end is when you took probability, did you do differentiating identities?
No. Oh, wait, so like,
Kind of, yeah. So differentiating identities. So this is one of the most useful methods in mathematics. It is a lot of work to create an identity. If I can give you a way to generate infinitely many new identities from one identity, this is good. Now, of course, you always have to justify, well, can I just interchange a derivative in the sum? Yes. Your certain conditions are met. And so imagine I give you a binomial random variable. So you have n and p. And so the probability you have k heads, can I call you in 5 minutes? So the probability that you have k heads, what would that be?
N choose k, p to the k, 1 minus p to the n minus k.
So the expected value of this random variable would be the sum, k goes from 0 to n, of k times n choose k, p to the k, 1 minus p to the n minus k. And you need to evaluate this sum to find the expected value. We start with p plus q to the n is the sum, k goes from 0 to n choose k, p to the k, q to the n minus k. And now we apply p d by dp. Because when I take the derivative with respect to p, a k is going to come down. And when I multiply by p, I'm going to restore things. And so I get n p plus q to the n minus 1 is the sum, k goes from 0 to n, of k, n choose k, p to the k, q to the n minus k. And in fact, I don't even...
Wouldn't there be an extra p on the left?
Probably. And did I take the derivative of this with respect to... Oh, yes, I'm multiplying by p. Thank you. Yes, thank you. And now what should I do?
So q equals 1 minus p.
Yeah. If q equals 1 minus p, then this is really easy. You just get 1 to the n minus 1. So you get np. And the other side is the expected value.
I always knew NP wasn't that complicated.
Yeah, well, if you drop the p, it becomes much easier. Everybody's always trying to show p equals np. I was trying to show n equals np. But you wouldn't let me do that. And so this is easy to justify because it's a finite sum. You can justify this for many infinite sums as well. This is a great way to calculate expected values, variances, and probability. It's a great way to create new formulas from formulas you already know. And so what is going on here is a powerful technique. And this is what we're going to need to use to do the analysis of runs, which we will do on Friday. And then we will, that probably will not take the whole class because I don't want to do all the algebra, you don't want to see it. And then we will do the Gauss circle problem and talk about what you expect that to be. All right.